Hello, so we're going to have a look at a question here, which is about magnetic fields and magnetic forces in a current carrying wire. So what we have here is we actually have a loop that's placed in the normal magnetic field of the Earth. The field lines here are shown in blue. These are our field lines. I'll just see if I can right in here. So our field lines are going this way and our loop is moving with 2.5 amps in that direction going around if we're looking down on it in a clockwise direction. What I would probably do just to answer this question is put down what we know. So we're going to put down that we know that our current here is 2.50 amps. Our magnetic field, okay, B is expressed as 6.50 times 10 to the 6 Teslas. This wire actually states that you have 10 turn, so a 10 turn current carrying wire. So that means that our N value is 10, and I'm just trying to think, and then we've got to talk about the length of the wire. Now, the length of the wire, all up, across a square, you're probably talking about 8 meters, but the wire is just talking about 2 lengths, and I'll go back and I'll talk about why specifically I'm discussing these 2 lengths. So we're just going to put the lengths as 2 meters. Okay. So we'll leave those links where they are. But we have a lot of information here. So what I'm going to do is read a couple of items from the question and then go through each of its part. So it says 2.5 amp current. We've already got that down. 10 turn carrying wire. It's expressed as WXYZ. Each side is 2 meters long. We've got that. The loop is within the magnetic fields at a point where the magnetic field lines are parallel to the Earth's surface and point geographically north. The field strength at this point is 6.5 times 10 to the negative 6. So I probably need to make that distinction. Teslas. And part A says which side of the loop is experiencing a magnetic force. So if I had a look at part A, and let's say that I just drew my loop looking from downwards. So the field lines are going across it. Okay, so this is my field and this is the loop, and the loop's having a current carrying that way. Well, if I use my right hand slap rule where the forces are going to be located, I don't have forces, so there's 0 forces where the wire is parallel with the field. All right, so that's an important thing to. So in this section here, okay, force equals 0, and force here equals 0. But when they're working perpendicular, so when I'm talking about this section and this section, we do get a magnetic force occurring. So we'll just get rid of that. And this is where we would use our right hand rule. So I'm going to show the direction of the force, because the force is either going to be into the page or out of the page, depending on which side that we're working on. But if I use into the page, okay, so my field lines are there, currents going, so my field lines follow the fingers, my current follows the thumb, and therefore in this section my palm would be open upwards. Just undo that. And so on this section, sorry, it shouldn't be that, the field would be coming out of the page, if you like, or the force will be coming out of the page. So we're saying that. And in this section, if I use my field lines as my fingers, my force going there, my palm will be shooting down, should be going down into the page, okay, and the force going down into the page. So which sides of a loop are experiencing a magnetic force? If I want to answer that question, okay, the sides that will be experienced are sides X to Y and Z to W, or you could say W to Z. I'm just following the direction of the current. Okay, so they're the forces that will be working on it. Question B says, determine the magnitude of the force exerted on each side of the loop experiencing a magnetic force. And this is where we use this equation, F equals I L N B. It could be written in a different way, okay? So you could write it as F equals N I L B. That's probably more traditional how it's working. And that's where we bring all our values here, where we have them all here, together to get the calculation. So number of turns, 10, current, 2.5, okay, the length, 2, so we got 6.5 times 10 to the negative 6 as our field strength. So 2.5 times 2 is 5 times by 10, so I'm going to have 50 times 6.5 times 10 to the negative 6. I'm going to put that into my calculator. So just bear with me for a moment because I'm just going to do the calculator work. Okay, and I get a force of 0.00035 newtons. Okay, you may want to write this as 0.35. Oh, actually, we won't write it like that. Write it as 3.5 times 10 to the negative 4 newtons. And then C, determine the direction of the force acting on each side of the loop experience a magnetic force. So if I drew the diagram as they have it written in the question, so I'm just drawing the diagram very similar to how they've represented it in the question, and this is where I use my right hand rule. Okay, so if I look at section X and Y, this section, current's running from X to Y, that will be the direction of my thumb. Fingers follow the field lines, therefore the force will be acting upwards. So X to Y, we say upwards. And then if we look at W to Z, well, the current's acting in the opposite direction, field lines, fingers follow the field lines, thumb follows the current, my palm should be acting downwards then. Okay, so W to Z should be downwards. And that's our answer.